Okay, we're going to have a quick look at Beer-Lambert's law, more simply known as Beer's law, and just going to quickly go through how the experiment is set up and the math behind it, enough basically for you to be able to answer these questions in a lab setting as well as on the exam. So I wrote that the Beer-Lambert's, or simply Beer's law, is a linear relationship between the absorbance and concentration of absorbing species. So the first thing we have to settle is what is absorbance. So different chemical species, when struck with light, UV visible usually, will absorb at some of the energy of the light, causing a difference in the intensity of the incoming light into the sample and the outcoming light or outgoing light as it shines through the sample. It basically is the effect that we can see just making a powdered drink like Kool-Aid, where the darker the Kool-Aid, generally the more drink crystals have been dissolved into it. So we first have this this ratio of the intensity of incoming light divided by the intensity of the outgoing light divided by the intensity of the incoming light, and that is called transmittance, represented by capital T, which can be confusing as capital T is used for other things as well. So absorbance is equal to the negative log of transmittance, or of that ratio I over IO. So basically we use an instrument called a UV vis spectrophotometer, which we can calibrate to measure a certain wavelength. Basically there's a monochromatic filter that is adjusted in the instrument, and basically how it works is you have your light source, it shines through your sample, and then there's some sort of detector, and somewheres in here there's your monochromatic filter that will adjust the wavelength. So the bulb's going to put out frequencies from like 400 to 900 nanometers, and the monochromatic filter will select just one of those wavelengths to measure the intensity in and the intensity out. So the law is really simple. It says A equals ABC, which so it should be fairly easy to remember. A is what we call the absorptivity coefficient. You can also see this written with epsilon, the symbol epsilon. But epsilon is the molar absorptivity coefficient. It's a very similar concept, but it's slightly different definition. B is the path length, usually measured in centimeters, but it would be dependent on what the units are with A. And C is the concentration of the sample. Usually we're dealing with moles per liter, but once again it would depend on the units on A. So here's how the technique would work. We have the instrument and we obviously plug it in, you turn it on to warm up for about 15 minutes, and then you adjust your monochromator, this thing, to a peak frequency. Now the peak frequency is dependent on what you're trying to measure. So the blue copper sulfate would be different than the reddish cobalt chloride, be different than the potassium chromate, which is yellow. So that is something that we basically will plot, and you get a kind of a peak. If you know anything about black body radiation physics, it's a similar concept. Basically what we're after is what is the peak frequency, and for cobalt chloride, which is what the example we're going to use today, that peak happens around 500 nanometers. So we have a curvette, and the curvette is laid out, usually it's a square. The ones I have in my lab are actually look like regular test tubes, they're just small. They usually have a mark on the front of them as indicated as a little line, and that little line will show us which way we should face it. And then every single time we wipe the test tube down, so a small test tube called a curvette, usually flat, we rinse it out with deionized water to make sure there's no contaminants in there from earlier. And basically the first thing that we're going to do is make up the solution with everything that we're planning on using during the experiment except the analyte itself. So for example, if we needed to add some sort of chelating agent, you need to add acid to make the solution, to make it better dissolve, all of that goes in except the analyte itself. Basically in the example we're going to use it would be everything except cobalt chloride. In a lot of cases the blank is just going to be just deionized water itself. There's really nothing else added. So then we make up standard solutions. So we make up a stock solution usually of the most concentrated species we want to measure. Um, and then we just dilute that into 3 or 4 different dilutions, getting obviously usually cutting the concentration by a third or a half each time. So we always start from when we go to take measurements of the most concentrated to the least concentrated. So we take the blank, we put it into the machine, we measure this transmittance or the I over IO as a reading of absorbance, and we then increase the concentration until we get to the most concentrated. Some instruments can have something called a memory effect, which if you measure the more concentrated one first, you could have problems, as well as in between each time where you rinse out the cuvette multiple times to make sure there's no contamination. When you get the absorbances, you plot on the x-axis, you're going to plot your concentration, and on the y-axis you're going to plot absorbance for your known standards from up here. You do plot the blank. There's 2 real methods for dealing with it. If you're the only one using your instrument, you can actually zero it out on the blank and then everything is relative to that zero. Or if you're in a lab setting where there's other people that are going to kind of be shuffling in, you can just measure your blank, record that value, and use it as your starting material zero concentration. So in which case you'll have a y-intercept, I guess, in your line. So then the next thing we do is we are going to actually make that line a best fit. Usually the best thing to do is to actually use graphing software for that, so your slope is well done. It's not just an estimate, but if you're stuck, you got to use an estimate. And then using the standard curve, we can actually interpolate the data for an unknown and find out what its concentration would be because it's directly related. So here's a little try this. It says a solution of cobalt chloride is made to standard solution. A UV visible spectrometer is set to measure light at 500 nanometers. So we've done a test and determined that is the peak frequency. For a standard curve, we're going to make a stock solution of 0.15 mole per liter using cobalt chloride hexahydrate. So the first thing we're going to do is how many grams of cobalt chloride hexahydrate do we need? So I'm just going to start and write 237 grams per mole is the formula weight of cobalt hexachloride. I want 0.150 moles per 1 liter, and then I want 100 milliliters of it. So my liters cancel, my moles cancel, and it's going to give me in grams, and I find out that that is 3.57 grams. So I would take 3.57 grams measured into a weighing dish, rinse it in, transfer it quantitatively into your volumetric flask, dissolve as much as you can, then make it up to the calibration line. Because you're setting standard solutions, you really want those concentrations to be spot on. You don't want to be kind of plus or minus. The more accurate you are on making up your standards, the better your results are going to be. So you make up the stock solution, and we're going to be making up 50 milliliter samples of each of these. We could do 25, but most labs would not have a 25 milliliter volumetric flask, at least ours doesn't. And we're going to use the concept of the concentration of the concentrated times the volume of the concentrated solution is equal to the concentration of the dilute solution times the volume of the dilute. So this is just your dilution factor. C1 V1 equals C2 V2, you might have heard it as. So if I want to figure out what the volume of concentrated I need to put into these volumetric flasks, I simply write the volume of the concentrated is equal to the product of the concentration and volume of the diluted substance divided by the concentration of the concentrated solution. So I'm going to plug my values in for my first one, my 0.12. So I want to make 50 milliliters up. My concentrate is 0.150. So I would need 0.040 liters. So for 0.120, I need 40 mils. And then I have 0.040 0.09, 0.06, and 0.03. So each time I'm going to basically just be decreasing by 10 mils. You can go through and do these calculations, but for the interest of time, we're just going to realize that those calculations would give you 30 mils, 20 mils, and 10 mils of solution. And you would put those into a volumetric flask and then dilute with deionized water, and now you have all of your standards and including a blank. So the next thing that we're going to do is we're actually going to look at the absorbance of standard solutions measured at 500 nanometers. So we have these values that are here. So let's zoom in on this table. So for each concentration, this is just what we made up above. And when we threw it into the instrument, these are the values we got. We'd usually do it twice and take the average of the two. The instrument in our lab only has 2 significant figures as an output, so this would be a little bit more accurate. Sorry, precise, a little more precise. So the question C says, if the curvette has a path length of 1 centimeter, what is the molar absorptivity constant? So you can see on my graph I have concentration in moles per liter as the x variable and absorbance as the y variable. I plotted my points and put a line of best fit. I did this on Excel already, and we can see that the slope is equal to 5.498 just from the equation. Noticing my r squared value is very, very close to 1, so this has a strong linear correlation. So I know that 5.498 is equal to A times B from Beer's law, ABC, where concentration was my x. Since B is equal to 1, 5.498 equals A. If I divide both sides by the constant by B, which again is 1 centimeter, which is indicated here, it's going to be the same number. The units on it should be molar to the -1, centimeters to the -1 would be what we would expect here. So for the last part of this, we know that we have our equation y equals 5.498x, 0.0093. Just from our line of best fit. So if we have an absorbance reading on an unknown of 0.2500, we have to remember that this is basically saying times 1 centimeter times the concentration. A equals A, B, C. Similarly, you can also just plug it right into the equation. That's usually what I do, because the offset here tells me that there was something that the water was absorbing at 500 nanometers, or the blank was. So when we plug that value in, you can use either this way or just plugging it into the equation. I'm just going to plug it right into the equation. So I have 0.2500 equals 5.498 concentration minus 0.093. Just rearranging and solving for C. C equals 0.062 moles per liter. So that's all we have to do now. Once you have the standard curve, imagine standardizing this for a particular analyte. Once it's standardized and it's not touched and it's running, of course you should calibrate every so often. You can continually run unknowns through relatively quickly, get the absorbance from the instrument, plug it into your calibration curve, and you'll know exactly what the concentration is. So we can just make sure that this makes sense. As we look back at what we've done a little bit earlier, the concentration of an absorbance of 0.25 is going to fall in right here, and it's kind of what we would expect, coming out 0.062, very, very close to this value here, as we actually putting it into the line and getting out the unknown concentration. So that is Beer's law.